But there is something very cool and very practical, right? It's not often these two things come together, right? But in the case of Burrows-Wheeler transform, it comes together, and we have something called a suffix array that is based on the Burrows-Wheeler transform that we can look at, that will further make the running time very efficient, and at the same time using this very interesting idea called this Burrows-Wheeler transform. Okay, so I mean, you will have to see it. Don't take my word for it. You'll have to see it to appreciate how elegant this transform is. But before we go there, let's just set up why we are looking at another data structure. We already have the suffix tree. Aren't we done? Aren't you happy with the suffix tree? Why do we need more, right? So I'm happy, yes, with the suffix tree because we have linear running time, we have linear space, but I'm not fully happy because this order, this big O notation, you may have seen in the earlier algorithms classes, analysis of algorithms, it hides constants, right? And sometimes these constants are very large. So in the case of suffix tree implementation, these constants are roughly 20 times the length of the genome, right? So 20 is this constant that is being hidden, right? So the implementations may require 20 times the length of a genome for space requirement, right? Let's just focus on space for now. So if your genome is 3 billion letters and you want 20 times 3 billion, right? So that is like basically 60 billion, right? So it may determine the difference between whether it fits on a very affordable cheap computer that sits on multiple clinics, or whether you need a large workstation with a large memory. I mean, you know that the memory, the random access memory, is the most expensive part of or one of the most expensive parts of a computer, right? So we'd like to keep our memory footprint to be as small as possible so that we can fit the whole genome or the index structure, the suffix tree or some other data structure that is an index for the whole genome, into the memory, main memory, right? So the question is, can we reduce this constant factor down to a much smaller number? Okay, and this is what we mean by the challenges of mapping billions of short reads to a very large genome, right? Every bit matters, and every second matters, or every millisecond matters in our running time, because we are trying to look for scalability that will make this technology much more accessible to all clinics, not just the clinics which have in across all countries, not just the clinics which have lots of resources, right? Okay. So how do we reduce this constant factor? And this is where this elegant idea of Burrows-Wheeler transform comes in. And like I said, let's see it, and then you will appreciate before I say anything more, right? Of its elegance. So it is a way, you can think about it as a way to compress the size required to hold a genome. Okay, we want to decrease the amount of memory required to hold the genome, and so we need to compress that. Okay, it seems like a seemingly separate problem, right? This compression, we are in the topic of pattern matching. What does pattern matching have got to do with compression? We'll later see that both are related, but for now let's just focus our minds on how to compress a large genome. Okay, one way to compress a string is using run length encoding, right? It's a very simple idea. If you have a genome that looks like all G's, all C's, all A's, and so on, then instead of repeating these letters G all the way, you just say there are 10 G's. So you have 10 and G. Here you have 11 C's. So instead of writing all of this C, 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 you just say 11C, 7A, 15T, 5C, 1G, and so on. Okay. This is called run length encoding. This whole stretch of the same letter occurring next to each other contiguously is called a run. So this is the first run. This is a run of 10 G's. This is the second run. This is a run of 11 C's. The third run is a run of 7 A's, and so on. And so you can represent these runs using this concept of run length encoding. Okay. This would have worked very nicely if the genome in fact looked like this. The problem is that genomes don't have lots of runs, right? So we can't really use run length encoding. But what happens is the genomes do have lots of repeats. Okay, repeats meaning that you may not have a run Let me just illustrate what a repeat is. We have already seen it before, but just to make sure. So you may have something called an ATG, and then you may have some other things, and then you may again have an ATG, and then you may have some other things, you may again have an ATG. So the ATG may be repeating multiple times in different parts of the genome. Similarly, different k-mers for some small k could occur in different parts of the genome, right? And then so these kinds of repeats can occur, and how can we exploit that property of a repeats? By converting the repeats to runs. Okay, so you take the genome, you convert it into some other representation, a transform genome, such that the repeats are converted into runs. Then you can store genome star using run length encoding. Okay, that is the idea. And this magical transformation of converting repeats to runs is done by this Burrows-Wheeler transform. Okay, that's what we are going to look at next. So we have lots of repeats, which we do have in many genomes, because biologically we have just observed those repeats. Okay, so without getting into why it is, there are a lot of repeats, and we come up with a transformation, a Burrows-Wheeler transformation, that will convert the repeats to runs in this genome star. And then we do a run length encoding so that we have a compressed genome for this genome star. Okay. And how do we do this step? And like I said, we are going to do the Burrows-Wheeler transformation, or BWT. And the way to understand that is the following. Okay. You have your genome Panama bananas, you convert it into a cyclic string. So you have PANA, BANA, right? You have PANA, MA, BANA, NAS dollar. So that you have written as a cyclic string, and you also now see why we need this dollar, to know where the starting letter is and where the ending letter is. Okay, so this dollar is quite helpful for that. Okay, so we have Panama bananas, and then we have this cyclic string. So then we want to make all cyclic rotations of Panama bananas. Okay, so we have Panama bananas, we have Anama bananas. Oh, actually they are going in the other way around. So we have Panama bananas, right? Dollar. Then we start with dollar and then say dollar Panama bananas, right? Then we have S dollar Panama banana. Then you have, start from this A here, AS dollar Panama bananan, right? And so on. So you just keep all the cyclic rotations of this particular string. Okay, I'm going to do all the way, and you stop when dollar has come to the last but one position, right? So you have done this cyclic rotation where each of these letters is put to the previous letter and you are shifting it. Okay, so this S goes here and then you are shifting it. That's how you get the next row. This A goes here and you shift it. That's why we get the next one. Okay, so I hope the process is clear. You write down Panama bananas dollar, and then you keep rotating it. You take the last letter, put it in the first, you shift it right, and then you keep that until you get all of your rotations. Okay, now the next step is, once you have formed all the cyclic rotation, you sort this lexicographically. Okay, so that is the key step here. You just sort this set of cyclic rotations lexicographically, and dollar comes first. Okay, what is a lexicographic sorting? It's just a standard way in which dictionary sorts the words. Okay, dollar comes first. That is a special symbol, so it always comes first. A comes before B, B comes before C, and so on. When you have ties, then you ignore all the tying, all the tied letters, and you look at the next letter which is distinct, and then you apply the sorting on that letter. Okay, so for instance, you can see here that there are many ends here, right? And all of these ends are tying, so these, you have to figure out what these locations are. So you look at the second letter. If the first letter of these cyclic rotations are tied, as in this N and N, this is a tie. So you look at the next letter, that is also a tie. right? So this first letter is also a tie, second letter is also a tie. So to break the tie, you go to the next letter, that will be M and S. Now these are all distinct, so you can then sort it based on M comes before N comes before S. Okay, that is why Nama Bananas $PA is coming before Nanas $Panama Ba or Nas $Panama Bana. Okay, so that is how these ordering of these three cyclic rotations are done. Okay. Similarly for all the other ones. So lexicographic sorting is simply the way in which dictionaries sort the words, right? And then we are following the same things. We look at the first letter, sorted based on the first letter. If there is a tie, you go to the second letter. If there is a tie there also, you go to the next letter, and so on until you hit some distinct letters. Okay. Okay. You can also see the role of the dollar. The dollar will make sure that none of these two rows are identical, right? Because you can see that the position of dollar in each of these rows is, let's say your genome is not Panama Bananas but all A's. The cyclic rotation, you don't have to worry about whether all of them will be identical. The dollar sign will be in the last position initially, then it will be in the first position, second position, third position, and so on, right? So this will make sure that all of these cyclic rotations are distinct. So you don't have to worry about ties in all of the columns. At least one column there you will find a distinct position, and you will be able to properly sort these set of strings. Okay. I want you to think about it in a bit and then see if there are any questions. Okay. So this dollar serves that purpose as well, to make sure that all the different cyclic rotations are distinct. Okay. And then dollar always comes first. That is the convention we are going to follow. Now, the strange thing is that the Burrows-Wheeler transform is going to take the last column of this particular matrix, and then that is going to be the Burrows-Wheeler transform of Panama Bananas. Okay, this is your genome, this is your input, and your genome star is going to be this last column here. Okay, so this last column here, SMN $A. That is going to be your Burrows-Wheeler transform. Okay, we took something like a genome and then made it into genome star using this Burrows-Wheeler transform. Okay, and then we are basically have not compressed anything yet, right? So because in the end we want to compress this thing, right? So why did we go through all of this effort? How can we compress it? Okay, let's just address that question. Why should we care to get this last column, right? And this is the reason why, right? If you apply this Burrows-Wheeler transformation to different sentences in a particular or different excerpts from a text, right? So then you will see that if there are many repeating words, I mean, like in the genome I said there may be some cases where ATG keeps on repeating or some other keyword keeps on repeating, right? In an English language also there are many common words and the and so on, right? That will also keep repeating. And if you consider a document as one long genome, right? And then you consider all possible rotations of this document, right? And then do a Burrows-Wheeler transform on it and look at the last column, you will see that the repeats have all been brought together, and then you have converted them into runs. And is the one that has been repeating in this document. It has been converted into runs of A's here. And there are some things like U which are occurring here, but more or less there is all of these ands which are occurring in different parts of the document have been grouped together, right? Because all of them are basically sorted based on their first few letters, right? And then the ties are broken according to the next letters. All of them are sorted based on that. Because of that, there are all possible rotations of and all the A's are brought together. Similarly, all the N's will be brought together, all the D's will be brought together, okay? And then if you look at the last column, it is always the previous letter of the first column, right? So like I said, you always take this, and this is the way that the cycle is arranged, right? So A comes, and then there is ND and so on. And then in the other case, you will have D, and then you will have A, and so on, right? So the last column, you will have all these A's from the AND grouped together. Similarly, all the N's, this is not shown here, all the D's, which is again not shown here, will all be grouped. Even for cases like common words like the, also the T, H and E will all be grouped together, okay? So we have converted repeats to runs through this process of Burrows-Wheeler transform, okay? I hope that part is clear. So that is the magic here, that the Burrows-Wheeler transform, which is the last column, is converting repeats to runs. So this may be n in length. If n is the size of the genome, this is also n in length. But then once you compress it, the idea is that this is much shorter, because this BWT of genome will have lots of runs. This we are assuming has lots of repeats. Okay. So if it has lots of runs, then we will have a much shorter compressed genome, okay? So we have successfully converted repeats to runs, and we have now compressed the genome, but then how do we get the original genome back, right? So is this a lossy compression or is it a lossless compression? Any compression algorithm, we should also have a decompression algorithm, right? We need to also be able to get back the genome from the compressed genome. So can we do that, right? And that is called inverting Burrows-Wheeler. Can the Burrows-Wheeler transform be inverted? Is it a lossy transform or a lossless transform? Can we get back the original genome if we are given only the Burrows-Wheeler transform? Or in other words, if we are given only the last column of that matrix of cyclic rotations that we had, can we get back the original genome string? Okay, let's just look at it using a simple algorithm first, and then try to make it more efficient as we go along. Okay, given a compressed run length encoding, we can always get the we can always decode the run length encoding. That is easy, right? If you have 11 A's, 2 C's, 3 T's, 2 A's and so on, I'll just put in 11 A's here, I'll put 2 C's here, I'll put 3 T's here, I'll put 2 A's here and so on, right? So a run length encoded genome can be converted into the original representation quite easily. So this part is easy, okay? So but given this BWT of genome, can we get back the genome? Okay, so that is really the question we are interested in. Like I said, this is really your BWT. Your genome currently is banana. Okay, can we get banana? And we don't have all of these columns. These are all hidden. We only know this. So this is our last column, which is our BWT of genome. Only this is known. All the others are hidden, okay? So now the question is, can we actually reconstruct all the other hidden columns? If we are able to do that, we will know what the genome is also, okay? Because the first one is just $banana, right? Okay. So this is the sorted list of, lexicographically sorted list of all the cyclic rotations of banana dollar, okay? And what does this last column says, or for that matter any column, right? That will tell you all the letters present in the genome and including the multiplicity. So this says that A is present 3 times, N is present 2 times, B is present 1 time, and dollar is present 1 time, right? That is all I know by looking at excuse me, the last column, okay? Using that last column, can I get the first column? I'll let you think about it for a bit. Using the last column, can I get the first column? I mean, currently all of these are hidden, right? So there is all of these first, all but the last columns are hidden, right? So all of these columns are hidden. But using this last column alone, can I get the first column? right? Remember that this matrix is the lexicographically sorted cyclic rotations of the whatever the genome is that we don't know currently, but some unknown genome. In this case, banana dollar, right? We know that lexicographic sorting will sort will be sorting the first column before it sorts the second column, right? That is how it works. And I know all the letters in the genome, so the first column is going to be simply the sorting of all these letters in this last column, right? So sorting all of these A N and B dollar AA will give me the first column of the matrix, right? So that essentially comes from the way in which this Burrows-Wheeler transform was done, right? We took all the cyclic rotations and sorted it. So because we sorted it, we know that if we know the last column, I know all the letters in the genome, and if I sorted that, I will get the first column also, okay? If I know the first column and the last column, then something interesting happens. We can also know the first two columns of this matrix, right? So now we have reduced this hidden columns by one more. So this is known now. This is also known now, but all of these are hidden. The middle ones are hidden. Now the question is, can I get the second column also, right? And to do that, all you have to understand is that I need to know all the tumors in the string, right? And I know that all of these are cyclic rotations, that A comes before dollar, this N comes before this A, this N comes before this A, and so on, right? So I can do a cyclic rotation and then bring the last column before the first column. Then I will know all the tumors in my genome. So I do this cyclic rotation, A to dollar, N to A, and so on. So I get A dollar, NA, NA, B to A, BA, and so on, right? So I get all the tumors in the genome, and then I know that again by the lexicographic sorting that the first two columns have to be the sorted order of all these tumors, right? Because we are using lexicographic sorting. You sort this, then this dollar is always getting a priority, so dollar B comes first. Then you have A dollar and ANN, those will come here, right? And then you have NA and NA, and those will, then you have BA, so that BA comes here, and then this NA and NA, that will come here, right? So this is being sorted, and now I know that that would be the first two columns of my Burrows-Wheeler matrix, right? Which is this, exactly you can see here, dollar B, A dollar A and AN, B. So if you look at just these first two columns, this is exactly the same as these two, right? So now I have increased the visibility. I mean, I've reduced the number of hidden columns by one more, and I know the first two columns and the last column, right? So all of these are identical, right? And you just have to iterate this procedure. I hope you have seen it by now, that if you now do one more cyclic rotation, I know all the three mers, and I can sort it to get the first three columns of the Burrows-Wheeler matrix, right? So now I rotate it again. Rotation is always the last string is put in front of the beginning. So you have A dollar B, similarly you have NA dollar, and so on. I sort them, I will get the first three columns of the Burrows-Wheeler matrix, right? And then I can iterate this procedure and I will get all the columns, okay? 4 mers, 5 mers, 6 mers, and I know all the columns. Now if I know all the columns, every row of this matrix will tell me, or any row of this matrix will tell me what the original genome is. I mean, just for simplicity, I can take the first row. Dollar is the final one, right? So I know that, I mean, if I know that the rest of the string, right? This is a cyclic rotation, right? So the rest of the string is going to be my genome. So banana is going to be my genome, right? For that matter, you can take any of these. So I can also take this last row. I can say dollar is my last one, so I will just take this BA and rotate it first. So I'll have BA, NA, NA, dollar, dollar, right? So that is going to be my genome. So once you know the entire matrix, like I said, you can take any row of this matrix and you can know what the genome is, okay? For instance, all the elements after dollar will give you the genome banana. So now let's just understand the running time and memory issues of this procedure. So reconstructing genome from BWT of genome required us to store, for instance, all of this matrix, right? So this matrix is again an issue. We have all n, if n is the length of the genome, all n rotations, and each of them is going to be of length n. So we have to store quadratic amount of space, right? So genome squared instead of just linear in genome. So can we invert BWT with less space? Okay, that is what we are going to look at next. Because always we want to, so think of the original problem with suffix trees. We were spending something like 20 times the hidden constant was 20. It was linear in the size of the genome, but it was 20 times the size of the genome, right? We want to do much less. Here we seems to have not done better because we are again going back into the quadratic problem. But can we actually invert a Burrows-Wheeler transform with less space? Okay, that is the question we will ask next. To answer that question, here is another elegant thing about Burrows-Wheeler transformation, but elegant and also a bit strange. Okay, what is elegant? Maybe I should clarify that clearly. What is elegant is that we were able to get only the last column of this matrix and somehow get all the other columns. If you started with any other column of the matrix, it would not have worked. Okay, that is an exercise for you for all the strings. Okay, but the last column of the matrix will give you the answer what the full genome is, and you will be able to reconstruct the full matrix for any string. Okay, that is the beauty about Burrows-Wheeler transform, right? In this Burrows-Wheeler matrix, it's the last column that is most important, right? And that is the magic where that is where the magic happens. If you know the last column, you don't need to know any other columns because you can do this procedure of sorting the 1 merge, sorting the 2 merge, sorting the 3 merge, and so on to construct the full matrix. Okay, but can we do this better than working with the whole matrix? Okay, so the matrix is nice to understand the concept, but in implementations we may not want to store the whole matrix. Okay. So can we invert BWT with less space? Okay, that is what we are going to look at. And the strange observation is that we have essentially excuse me, we are going to relate the first column and the last column. Okay, the last column is where the magic happens, and the first column is also in some sense important in this more efficient way of inverting our BWT. Okay, so we are going to look at all the A's in the last column and all the A's in the first column. Okay, and the claim is that there are 6, in both of them you will have the same number of A's because every column will hold all the letters including the multiplicities of that letter in the genome. So the first column and the last column will have the same number of A's. That is a simple observation, but the strange observation is that there is a 1-to-1 correspondence between them. So the A in the first occurrence of the A here, right, that is going to be matched to the first occurrence of this A here. The second occurrence of the A here is going to be the second occurrence of the A here. So there are going to be a 1-to-1 correspondence between the order in which these A's appear. So what do I mean by that? So if you look at this A and A, that is going to correspond to this, both of them are going to correspond to this single A in the genome. Okay, both this A and this A are going to correspond to this A. It's not like this A will correspond to this A and then this second A will correspond to some other A, right? That is not going to happen. The first A here and the first A here will correspond to the same A here, okay, not to some other A's. Similarly, the second A's correspond to this particular A, okay. The second A in the first column and the second occurrence of A in the second column, both of them correspond to this particular A in the string, okay, and not to multiple types of A. So all of them are the same, the third to the third, because you can see here, right? So this is $P, and then you look at the cyclic rotation. So this is $PA, right? And here also $PA, right? So this $PA is here. So this A correspond to both this A and also this A. Okay, let's keep going through that, and let's look at the fifth A. So this is the A that occurs before the second one from the last. So A and A is dollar, right? Here also, so this is the first A that is occurring, second A that is occurring, third, fourth, fifth, and sixth. Let's also look at here 1, 2, 3, 4, 5, and 6. The fifth A that is occurring here, A, again you will have to rotate it, and you can see that this is A and A is dollars. So this is the same A here, A and A is dollar, right? So this ANAS dollar and ANAS dollar are both, this blue A is the same A, and that is this ANAS dollar, right? So this A and this A are one and the same, right? Similarly, the sixth A will also be the same. The sixth A occurring in the first column and the sixth A occurring in the last column refer to the same A position in the genome, okay? Are both referring to the same position in the genome. And that is not true for A's alone, that is true for N's as well. There is a first N indicated as green, the second N indicated as red, and the third N indicated as blue. And their order green, red, blue, and green, red, blue, their order is the same in both the first column and the last column, okay? Now the question is it just a lucky thing that happened for bananas and A's and N's that we have seen for this example alone, or is it true in general? Okay, what about this property that the correspondence between the many times in which a particular letter occurs in the first column and the many times and the same number of times it occurs in the last column, are they always going to be in this one-to-one correspondence and in the same ordering? Okay, is it true in general? Okay, we are going to use the property that these strings are sorted, these cyclic rotations are sorted, to try to answer this question in the positive, that yes, it is true in general. Okay, and how do you see that? If you take all of these strings 1 to 6, all of these are sorted, so you can chop off the A, right, and then you can just add it to the end. So if you chop off the A, these are still sorted, okay, and because A is a common one in lexicographic sorting, if there is a tie in the first column, right, if there is a tie in the first column, then all the remainder part of the string is used to sort, right? So if all of these we know are sorted already, and so if you chop off the A, this is again sorted, okay, and you add the A back to the end, these are again still sorted, right? These are still sorted, right? And that is exactly what is the A occurring in the last column is, right? So each of them are occurring in these different parts in the last column, right? There may be something else like so you can see here that this is corresponding to this to this, this to this, this to this, right? Nana's dollar, Na's dollar. There may be some extra things like this P which came in, right, which don't have an A in the end. That is okay, but then if you ignore such things, then there is a one-to-one corresponding. These lines don't cross each other, right? So basically all of them are, because they are still sorted, right, you don't have to shuffle them around and make the lines crisscross each other. They are still sorted. Because of that, the ordering does not change, right? So the ordering in the first column and the ordering in the last column does not change, okay? So basically that is the key here, to notice that when you chop off this A, the ordering does not change, and if you add this A to the end also, it is the same A's in the end, so the ordering still does not change. So the last column, the ordering of the A's do not change. They are just wherever they are as in the first column, right? And so because of that, this last column ordering remains the same. There may be some other strings which are inserted. They may not all be contiguous. That is okay, but the ordering does not change. Okay. I want you to think about it a bit and then see if you are fully convinced. This needs a formal proof, but this is the framework of the formal proof. We are going to just leave it at this illustration. Okay. But let's just make the property more this strange observation more concrete. So this is, we will call it as the first class property. The kth occurrence of the symbol in the first column, for instance, if k is 5, the fifth occurrence of the symbol A in the first column, right? and the kth occurrence of the symbol in the last column, A5 in the last column, correspond to the same position of symbol in the genome, right? This is what always we have been saying, okay? So A5 here is the second A from the end, ANAS dollar, and the A5 in the last column here is also the same. It is ANAS dollar, okay? That corresponds to the second A from the dollar sign, okay? Those two are exactly the same position in the genome, okay? This is going to make our life much easier in inverting our Burrows-Wheeler transform, okay? So how is that possible? So we will invert a Burrows-Wheeler transform going in the reverse direction, okay? Like we will start with the last letter dollar, and then we will go recover one letter at a time, the letter before dollar and the letter before A and so on, okay? We are going to go recover the banana in the reverse order, okay? We will start with dollar because we know that dollar is always the last symbol, okay? So we will, the reason that we reconstructed in the reverse direction is that we know dollar is the last symbol, so we want to start there and then start getting all the other symbols. We start with dollar. Dollar only occurs one time, right? There is no $2 in the string, so that dollar and the dollar in the last column are always going to be the same. So so this dollar and this dollar, no special processing is required. So I know that before the dollar, the one letter that appears is going to be S, right? Because the cyclic rotation always goes in this direction, right? So we have S, which is our letter before dollar. So there is a dollar, one, and then there is an S, which occurs only one time, so S. Now I want to know what occurs before S, right? So then I have to look at this first column where S is, and then I'll have to look at what is the last column of that S1, okay? So I will say that this S occurs only once, so S1, so that corresponds to this S1, and so the letter before S is A, right? So then A, but then this A is occurring multiple times, but because I know that this is the sixth time this A is occurring, I can go back to not any one of these A, but I can precisely go back to the sixth A, okay? So that will make this procedure much faster, because otherwise if I don't know that this A corresponds to this A, then I'll have to try all possible A's, right? And I have to do something to figure out which A it is. But this first loss property will ensure that I once start with this $1, then I go back cyclic rotation of this, right, to go back to this S1, and then I go back to this A6. This is my A6. Then the letter before me, which I do not know, but I'm trying to figure this out one at a time, right, is going to be this N. And I don't want to wrongly choose this A, for instance, and say it is going to be M, right? But I know that this is this A, and so the letter is going to be N. And this is going to be N3 also. This is the third time the N is occurring in the last column. Okay, so I keep on going. So then this is this A6. Then I go to N3, right? Then N3 is going to be over here. So I'm going to come and say that before N I'm going to get an A, right? So this is N3. Then I have an A5. And A5 is here. I will get an N2. N2 is here. I will get an A4. And so you can see that I'm going and reconstructing the string in the reverse direction. Once I write everything down, I'll have a dollar S A N and the blue A here. Then I will get a B. Then I will get an A, and so on, all the way till P, and I will get Panama bananas. All right. Let's go through this. So we'll get a B1. B only occurs once, so that is easy. The first column there is a B, then you go to A1, then you go to M1, A2, N1, A3, P, and you're done, because that will go back to dollar, right? And your memory is that all these internal columns, no need to store. Only the first column and the last column you need to store, right? All the other columns you don't have to store. And so the size is 2 times the number of genomes, so there is order of number of genomes. It's still linear in the number of genomes, but it is just the 2 columns that you need to store, okay? So that is much better than 20, but are we keeping track of everything? How do we know? We haven't really addressed the original problem of pattern matching, right? And that is where this particular slide comes in. Why should Sun care? What happened to pattern matching? I mean, you went into this digression of I need to reduce the space required to store a genome. For that we need to do compression and we need to do run length encoding, but Burrows-Wheeler transform will make it easier to do run length encoding, right? But if we need to do Burrows-Wheeler transform, we need to somehow also know how to invert the Burrows-Wheeler transform, and that we are now able to do in order of 2 times genome time, right? But then what is all about pattern matching? I mean, let's get back to pattern matching. Can we use the Burrows-Wheeler transform, the first and the last column, to do actually pattern matching, okay? Given a pattern, find if it is present in the genome using the first and last column of the Burrows-Wheeler transform, okay?